All right, today we're jumping into one of the wildest and honestly most beautiful ideas in all of physics. It's the story of a cosmic glitch, a kind of flaw in our theories that, it turns out, isn't a flaw at all. In fact, it's so essential that the universe as we know it couldn't exist without it.
So here's the mystery we're unpacking. How can that even be possible? It just feels wrong, right? A bug in the system that's actually a core feature? This is the incredible paradox of what physicists call chiral anomalies, a super strange quantum effect that really forces you to rethink what a perfect theory of nature even looks like.
And this statement, it really gets to the core of the problem. You see, on one hand, these anomalies break a sacred rule in physics, something called gauge invariance, which you can just think of as a fundamental rule of consistency. But on the other hand, they make things happen that we actually see, like a particle called a pion decaying. So the big question is, how can the universe just break its own rules and still work perfectly? Well, to figure that out, we need to take a look at the rulebook itself.
Okay, to really get this, we gotta back up a little. Before we dive into all the quantum weirdness, you have to appreciate the beautiful, almost perfect world of classical physics and its most important idea.
So what do we even mean by symmetry in physics? Well, put simply, it means that the laws of nature don't care about certain changes. You know, if you do an experiment today and then do the exact same experiment tomorrow, you expect to get the same result, right? That's a symmetry. And these symmetries are incredibly powerful because each one is directly tied to something that must be conserved, like energy or momentum.
You know, in the world of classical physics, think Newton. This is an absolute ironclad rule. Symmetries are perfect. They're elegant. They just have to be preserved. No exceptions. This was seen as a foundational truth, the very bedrock our understanding of the cosmos was built on. But then, quantum mechanics showed up, and it basically took a sledgehammer to that perfect foundation. And this is where things get really, really weird. Down at the tiniest, subatomic level, those beautiful, simple rules of the classical world, they just start to fall apart.
Yeah, this slide just lays it all out. On one side, you have the classical dream, perfect, unbroken symmetry, always. But on the other side, you have quantum reality, where that same beautiful symmetry can just shatter. And this breakdown has a name. It's called a chiral anomaly. It's a fundamental glitch in the quantum code.
Now you might be thinking, okay, this is some weird math thing, but no, this glitch has totally real consequences we can actually see. It's the reason a particle called the neutral pion can decay into 2 flashes of light, something we see in our experiments all the time. It also forces other particles, like neutrinos, to behave in certain ways. This isn't a mistake in the math, it's a description of how reality actually works.
And if you want to know exactly where this all goes down, the scene of the crime, so to speak, physicists have pinpointed it. It happens inside a very specific quantum calculation, shown by something called a triangle diagram. This calculation, worked on by Adler, Bell, and Jacques, is pretty much the mathematical smoking gun.
So you can imagine physicists were kind of scratching their heads at this point. A fundamental rule of the universe was being broken, but the results were real. Was their entire theory just wrong, or was this flaw actually pointing to something much, much deeper?
And yeah, figuring this out wasn't easy. It took time. The problem was first really nailed down back in 1969, but it took about a decade for people like Fujikawa to find a new way of looking at it, showing it was just an unavoidable part of quantum math. Then an absolute legend, Gerard 't Hooft, came along and figured out the rules for how a theory could even have these flaws and still make any sense. And this was the huge breakthrough. The moment everyone realized the anomaly wasn't a mistake in the theory. It wasn't a bug. It was a feature. It was nature's way of telling us that there was a more profound, hidden rule that the universe had to follow.
And that deeper rule has a name: anomaly cancellation. The basic idea is that a theory is allowed to have all these little symmetry-breaking glitches, but only if they all magically conspire to cancel each other out. It's like having a bunch of positive and negative numbers that, at the end of the day, have to add up to exactly 0 for the whole system to be stable.
Okay, stick with me, because this is where it gets absolutely wild. Our best, most successful theory of reality, the standard model of particle physics, is actually riddled with these anomalies. Our entire understanding of the universe's fundamental building blocks is only mathematically possible if this incredibly delicate cancellation happens perfectly. And when you run the numbers, the math is incredibly specific. For this perfect cancellation to happen, the universe needs a very precise list of ingredients. It needs exactly
3. 3 generations of matter particles. Not 2, not 4, 3. This quantum flaw doesn't just describe our universe, it literally dictates its fundamental structure. It's mind-blowing.
So this is way bigger than just one clever fix for one theory. The discovery of these anomalies and how they have to cancel out revealed a deep principle that we now see echoed across totally different fields of science. It turns out the very same math, the same concepts, pop up in places you would never expect. Particle physics, okay, that makes sense. But then, in condensed matter physics, they explain the bizarre behavior of these exotic materials called topological insulators. And in pure math, they connect to these incredibly deep ideas called index theorems. It's the same pattern everywhere.
So, at the end of the day, what started out as this really annoying problem, a glitch that broke a beautiful rule, it turned out to be one of the deepest organizing principles we've ever found. It's like a cosmic proofreader, making sure the entire story of our universe, from particles to materials to pure math, all adds up and makes sense. The flaw is the feature.
And that just has to make you wonder, right? If this one perfect flaw showed us something so profound about the cosmos, what other mistakes in our current theories aren't mistakes at all? What other glitches are just clues pointing the way to a whole new level of understanding reality?